SPC is a control system which uses statistical techniques and is an effective method in preventing defects. It also supports continuous quality improvement. Here you will learn about how the process involves people, machines, materials, methods, management and environment working together to produce an output, such as an end product. Controlling a process is guiding it and comparing actual performance against a target. Then identifying when and what corrective action is necessary to achieve the target. SPC was created for the analysis of observational data. Observational data are a byproduct of routine operation. These data may be deliberately and intentionally collected, but they are collected while the process is operated in an ordinary manner. Observational data simply track the underlying process while the input variables are usually held constant. SPC is meant to be used on the shop floor, in real time, by operators whose tasks include collecting data and responding immediately to out-of-control situations. SPC supports a process in many ways. It is used as a control and monitoring tool. It also supports in triggers and differentiates between correctable and chance causes. It reduced the need for 100% inspection and makes us to understand a lot about the process itself. All natural processes are affected by intrinsic variation. In nature, no matter how hard we try, there can never be two identical actions that generate exactly the same result. Surprisingly, most of them also follow a normal distribution, where more outcomes are concentrated in the center and sparse to the edges. There are two types of causes that affect the process. One is the chance cause and the other is the assignable cause. Natural cause variation is fluctuation caused by unknown factors resulting in a steady but random distribution of output around the average of the data. This common cause variability is a source of variation caused by unknown factors that result in a steady but random distribution of output. This cannot be controlled by the operator or the doer. Common cause variation is also a measure of the process's potential and is also called random variation, noise or non-controllable variation. Assignable causes of variation are not random. Some examples of assignable causes are a machine in need of repair and defective raw materials from our supplier. They usually relate to some defect in the system or method. However, this failure can be corrected by making changes in a certain method, component or process. As you have learned in the lesson 1 on process, the controllable factors and the inputs are some of the reasons why the variations in the output data occurs. However, this is not random, hence it shall evolve as a pattern and show out the causes that result in the non-random pattern. Common causes of variation are random, which means that there is not a specific reason for the variation, such as a malfunctioning machine. The non-controllable factors such as the inherent fluctuation are all reasons why it results in this variation. When we measure the process, we take samples and analyze the sample statistics. This will result in a distribution like that is seen here. These are called the data distributions. There are many types of distributions, like the normal, bell-shaped distribution, but distributions do differ in terms of central tendency, or called the mean, and also the standard deviation or variance. It is also critical that you have a look at the shape of the distribution. If only natural causes of variation are present, the output of a process forms a distribution that is stable over time and is predictable. So when you are controlling a process, the data needs to be collected over a reasonable period of time. The inferences should be drawn only after the results are verified over a long range. To measure the process, We take samples and analyze the sample statistics following these steps. If assignable causes are present, the process output is not stable over time and is not predictable. The size of the sample used per subgroup in the control of a process via SPC has a direct influence on how well the process average is maintained on target. Larger samples per subgroup place a tighter control on the process by decreasing the width of the control limits. Depending upon the process control scheme, capability, sampling cost, and risk of non-conformance, an increased sample size per subgroup may be warranted. For processes where sampling costs are reasonable, many industries use 4 to 5 samples per subgroup. The control charts are evolved based on samples and are constructed from historical data. The purpose of control charts is to help distinguish between natural variations and variations due to assignable causes. If you see in this control chart, it acts like a traffic light, highlighting to the operations user when to warn, when to trigger and when to keep continuing. In SPC, samples of product or services are plotted on the control chart over time. We then interpret the chart to determine whether the variation in the process is normal or abnormal. We need to use the chart because most products and services exhibit some variation. If the variation is normal, the process is assumed to be in control. Therefore, we do not need to fix the process. If the variation is abnormal, this process is assumed to be out of control. Therefore, we need to determine what is causing this variation, such as a malfunctioning machine or untrained worker. The data itself may be categorized here as 2 types, variable and attribute. Attribute data is qualitative data that can be counted for recording and analysis. Examples include the presence or absence of a required label, the installation of all required fasteners said as yes or no. Attribute data are usually collected when standard measurements are difficult to obtain. Continuous variables can have an infinite number of values, but attribute variables can only be classified into specified categories. The advantage of variable measurements is that they usually give much more information. The advantage of attribute data are that they are usually easy to collect. A disadvantage of attribute data is that they are usually subject to appraiser interpretation. For example, one appraiser may define a chip defect differently from other appraisers. The means of large, random samples are approximately normal. The central limit theorem is a fundamental theorem of probability and statistics. The theorem states that the distribution of, which is the mean of a random sample from a population with finite variance, is approximately normally distributed when the sample size is large, regardless of the shape of the population's distribution. A population that follows a uniform distribution is symmetric but strongly non-normal, as the first histogram demonstrates. However, the distribution of 1000 sample means from this population is approximately normal because of the central limit theorem, as the larger histogram demonstrates. This histogram of sample means includes a superimposed normal curve to illustrate its normality. A sampling distribution describes the likelihood of obtaining each possible value of a statistic from a random sample of a population. In other words, what proportion of all random samples of that size will give that value. If you know the population, you can determine the sampling distribution. But you can still derive useful information about the sampling distribution without knowing the population. For example, even if you don't know the population, you might be able to say that there is an 85% certainty that the sample mean is within a certain number of standard deviations of the population mean. Or you might be able to say that, if the means of 2 populations are equal, The difference between sample means should fall between certain values. A simple way to collect data is by using a tally chart. Suppose you list down the characteristic value that is measured over a sample of values it is measured, then the tally marks helps in grouping them and form a frequency chart. An XBAR chart is a control chart for variables and plots the process mean, the XBAR chart, and process range R chart over time for variables data in subgroups. This combination control chart is widely used to examine the stability of processes in many industries. A control chart is a diagram with a center line, an upper control limit and a lower control limit. The upper control limit is normally equal to the mean of the sample data plus 3 standard deviations. The lower control limit is normally equal to the mean minus 3 standard deviations. If an observation falls above the upper control limit or below the lower control limit, the process is assumed to be out of control. The XBAR chart and the R chart are displayed together because you should interpret both charts to determine whether your process is stable. Examine the R chart first because the process variation must be in control to correctly interpret the XBAR chart. The control limits of the XBAR chart are calculated considering both process spread and center. If the R chart is out of control, then the control limits on the XBAR chart may be inaccurate and may falsely indicate an out of control condition or fail to detect one. Control charts are used to regularly monitor a process to determine whether it is in control. When it is not possible to measure the quality of a product or service with continuous data, attribute data is often collected to assess its quality. The most common chart for attribute is P chart. This chart is used when a product or service is characterized as defective or not defective. The P chart plots the proportion of defective items per subgroup. U chart. This chart is used when a product or service can have multiple defects and the number of defects is counted. The U chart plots the number of defects per unit. Statistical process control is an industry-standard methodology for measuring and controlling quality during the manufacturing process. Quality data in the form of product or process measurements are obtained in real time during manufacturing. This data is then plotted on a graph with predetermined control limits. Data that falls within the control limits indicates that everything is operating as expected. If data falls outside of the control limits, this indicates that an assignable cause is likely the source of the product variation, and something within the process should be changed to fix the issue before defects occur. To summarize, statistical thinking is needed as all work occurs in a system of interconnected processes. Therefore, understanding relationships helps in solving problems. Industrial problems needs statistical tools to prioritize, go deeper, filter, and make choices, and also to conclude and take decisions. Choosing the vital few to focus is crucial for any organization's survival. Variation exists in all processes. Minimizing the variation reduces cost and increases revenue. This understanding and reducing variation are keys to success.